To the second session of the second day of the largest strings conference ever in the entire history of the Earth, if not the universe, because other civilizations might have discovered string theory. So the first speaker of this session is Chi-En. The title is D-instanton calculus in SQL1 string theory. Please, you have 40 minutes.
Thank you. Thanks a lot for the invitation to speak. So I will talk about D-instantons in SQL1 string theory. This is based on work I did last year with Bruno Balthazar and Victor Rodriguez. As Ashok has already alluded to earlier today, our usual formulation of string theory based on the worldsheet is thought to be a perturbative expansion, a genus expansion. And that's what usually referred to as a string perturbation theory. Now there's of course the question of whether it's asymptotic series and maybe we need to resum the series. But it's widely known by now that this is not expected to be the complete story. And there's supposed to be non-perturbative effects. There's a so-called D-instantons, which are deep brains localized in space and time, as in this picture on the right here. And from the worldsheet perspective, they're supposed to give rise to boundaries. So you have a closed string, vertex operator insertion, and the boundaries of the worldsheet that end on the D-instanton. And it's expected that there are such diagrams that will contribute to just the closed string scattering amplitude. It is not understood in entire generality how to really amend the perturbative series by the D-instanton effect, even though it's understood in many examples that D-instanton effects are there and are important. So that's why there's the quotation mark on the plus sign here. And that's going to be the theme of this talk. And of course, it's also widely known that there are supposed to be gravitational instanton effects, which are suppressed not by e to the minus 1 over gs like D-instantons, but e to the minus 1 over gs squared. I will not have as much to say about that in this talk, but as you'll see, in the context of SQL1 string theory, to the extent I will be discussing, these e to the minus 1 over g string squared effects seem to be absent. Now, as I mentioned, there is no, as far as I know, first principle derivation of the D-instanton prescription in string theory. This is in contrast to the situation in quantum field theory, at least those with a semi-classical path integral formulation. You can point to the path integral, you can see that the settle point, and you can discuss the contribution from the region near the settle point in the field configuration space. We don't have that, the analog of that in string theory or string field theory, for good reasons. But it's expected that if you follow our notes, we anticipate the following structure of contribution of D-instantons. That is, well, we have some D-instanton configurations, say in type 2B superstring theory. There are point-like objects in space and time. There's a moduli space of them, and we're supposed to integrate over the moduli space, so the elliptic coordinates of D-instantons. And then we're supposed to, the integrand is supposed to be the sum of all diagrams of the worldsheet with boundary. So they will involve diagrams of different topology with closed string insertions. And then there are these kind of empty diagrams, diagrams with that are worldsheets with boundary but no closed string insertion, that are responsible for both the exponential suppression by e to the minus instanton action, as well as some correction to the instanton measure, which we'll discuss in some more detail. And as Ashok also mentioned, there's the overall normalization, which because we don't have a path integral derivation of this kind of formula, we don't know how to fix it a priori in string theory. But in various situations of interest, this overall normalization can actually be fixed by indirect argument by matching the answer with duality. This is the case in both type 2B string theory and as we'll discuss in the SQL1 string theory, the 2D string theory. And another important feature, important subtlety about this is that there are divergences. This was also an important part of, well, essentially the key part of Ashok's theme of Ashok's talk. The divergences due to open string modes of on D-instantons. The cancellation of these divergences from diagrams of different topology. This this kind of phenomenon was understood by Fisher and Susskind in the closed string context and extended to the D-instanton case, essentially, by Joe Pochinski already back in '94. And a full treatment of this does require open plus closed string field theory. But in this talk, I'm going to try to take a shortcut. So the goal of this talk is to learned the rule of D-instanton computation in C=1 string theory, also known as 2D string theory, from the worksheet perspective, guided by a non-perturbative completion of the dual matrix quantum mechanics. Why C=1 string theory? Well, this is a very nice model of bosonic string theory. In fact, it's the only known bosonic string theory that admits, some nice things that you would like to have: a worksheet description, a worksheet CFT coupled to BC ghosts, a space-time interpretation. Let me emphasize time here. Unlike C=1 string theory, it does not have time, and it has a consistent quantum perturbation theory. This is unlike the so-called critical bosonic string theory, which is in 26 dimensions, but it does not exist at a quantum level. This C=1 string theory is was once a very hot topic in string theory as a whole, and it was thought to be defined perturbatively, but defined beyond level perturbation theory. I claim that is not the case. In a part of the goal of this talk is to actually extend this beyond perturbation theory. So let me remind you that the worksheet description of C=1 string theory involves a time-like boson, the C=25 Livio theory, and the usual BC ghost system. The Livio, just to set up the notation, the Livio is often described by some action with the Livio field phi, which can be thought of as parameterizing the space, the target space, and there's some background charge Q for this Livio field, and so there's a semi-classical description of Livio theory which is valid when this background charge of Livio theory is large. But here we're going to take this limit Q goes to 2 or B goes to 1. The center charge is 25. This should be viewed as a strongly coupled conformal field theory. In Livio theory, the states or equivalently the vertex operators in the level of CFT should be thought of as scattering waves of the Livio potential in the target field space. I will denote a family of vertex operators of Livio theory, which are essentially, in fact, the complete family of Virasoro primaries in Livio theory by VP. These are scalar operators labeled by a parameter, which is a positive real number, also known as the Livio momentum. Now the theory is strongly coupled, so I cannot, write a exact expression of VP in terms of normal ordering. But what I can say as a defining property of this operator is that in the asymptotic region of the target field space where phi goes to -infinity, where the Livio potential dies off, that's also going to be related to the asymptotic region of C=1 string theory. This VP looks like a linear combination of incoming and outgoing wave. The shift of Q is due to the background charge. Now the incoming and outgoing wave differ by a phase, which is a reflection phase of the Livio potential. As the square root of the space is historically known as the Legpol factor. But for my purpose, it will not play any role. So this VP is a naturally normalized, delta function normalized the spaces of primary operators of Livio theory that naturally has delta function normalized 2-point function. The complete set of closing asymptotic states, in and out states, which are labeled by either plus or minus here, are constructed out of this Livio primary VP and combined with each of the I omega x naught in the time-like boson part. And the dispersion relation is so that this operator is on shell or corresponds to a BRC cohomology representative. Asymptotically, as you can see, it obeys a sort of a massless dispersion relation in 1+1 dimension. So the content of the theory is that of a scattering of particles off the Livio wall that also interact with one another that asymptotically behave like massless particles 1+1d. It's well known that there's a dual matrix quantum mechanics, which can be equivalently formulated as a certain scaling limit of a system of infinitely many free fermions. Each fermion is governed by a non-relativistic Hamiltonian, p squared minus x squared. So there's a potential v of x here. The closed string vacuum is thought to be, at least at the perturbative level, a Fermi C that fills the right side of the potential up to energy minus mu from the top of the potential. In the phase space, it's this hyperboloid region this shaded region over here. Now, the closed string states, in this duality, the closed string states are not due to the fermions themselves, but rather they're due to the collective excitations of the Fermi surface. So there's some wiggles on Fermi surface that effectively will be interacting quantumly. And they can also be equivalently described in terms of particle-hole pairs. You have the excited fermion, it leaves a hole behind. So these particle-hole pairs are an alternative and precise, in fact, description of the collective excitations of the Fermi surface in this theory, and they're supposed to be dual to the closed string asymptotic state. In my convention where h bar is equal to 1, the height of the potential, this minus the Fermi energy, which is this parameter mu here, is proportional to the inverse of the string coupling. So when mu is large, the density is high, the system becomes classical. When mu is small, it becomes strongly interacting. Okay, so it is well known that there are many papers on the subject from the early 90s. I will not list all the references, but I want to mention this paper of Moore, Plesser, and Regulum, which formulates amplitude in a way that is convenient for the generalization I'll be discussing in this talk. These closed string states, or the collective excitations of the Fermi sea, can be thought of as particle-hole pairs, as already mentioned, and their scattering can be understood entirely as a scattering of particles and scattering of holes. The non-trivial interaction having to do with this kind of Bose-ionization a relation that relates particle pairs to the collective excitations. Okay. Now, here I use this RP to represent the reflection amplitude of a particle, which is the fermion themselves, and RH to represent the reflection amplitude of a hole. Now let me emphasize that the original fermion system is free. So the RP, the reflection amplitude of the particle, the fermion, is just the standard non-relativistic quantum mechanics of a particle bouncing off the potential. There's some amplitude of tunneling to the other side, but most of the particle will return. There's amplitude of the scattering of the particle, which you can calculate in non-relativistic quantum mechanics. The reflection amplitude of the hole, on the other hand, depends on it's a property of the system collectively. It depends on what is the Fermi surface and how precisely you define the hole state. And that's the question. That's the place where we'll have some ambiguities potentially in how we would non-perturbatively complete the system, because obviously, if you fill just the right side of the Fermi sea, that's not going to make sense at a non-perturbative level, because due to the tunneling of the fermions to the other side of the potential. So you say that different proposals of this non-perturbative completion of the matrix quantum mechanics has been considered in the past, and the point of view that had been taken for some time was that anything goes, because as long as you maintain the same perturbation theory, any kind of non-perturbative completion of the matrix quantum mechanics should define a sensible non-perturbative version of C=1 string theory. However, as I mentioned from the beginning, in string theory, we kind of have some sort of idea of what the some non-perturbative correction should be. That these D-instantons should be captured by this worksheet with boundary, and we should have a way to classify what are D-instantons. So it's not like we don't know anything at all about the non-perturbative completion of the closed string amplitude beyond the genus expansion. Now you can ask whether that would agree with any way of non-perturbative complete this matrix quantum mechanics that you would come up with. So for example, here's a possibility. So the one thing you can do is to simply say that the potential, well, instead of going down the other side, there's some wall. Okay. So this will lead to some non-perturbative version of the reflection amplitude of the particle as well as the hole, based on relation. In this case, the reflection is completely unitary in the non-relativistic quantum mechanical system. So based on relation like this. This turned out to not satisfy what I would like to do, which is to match with D-instanton computation on the worksheet. This alternative proposal has been considered in the literature, which goes under the name of type 0b matrix quantum mechanics. It's due to is understood to be due to a different 2D string theory, which has supersymmetry on the worldsheet, the type 0B string theory. This quantum mechanics, it has the same, Hamiltonian for the free fermion, but you have a different choice of vacuums for the closed string. You fill both sides of Fermi C, which seems to be very natural. In this setting, one can show that, in fact, this was already considered in the early 90s. One can show that the reflection amplitude of the hole is, in fact, just a complex conjugate of the reflection amplitude of the particle. And both of them has modulus that is slightly less than 1 because of tunneling. Okay. It will turn out that this thing, which is a consistent matrix model, of course, by itself, also does not agree explicitly with the D-instanton effect in Siegel-Swan string theory computed from the worldsheet. What does well agree is what I refer to as the non-perturbative Siegel-Swan matrix model. So this again has the same Hamiltonian, and the modification is the minimal thing I would like to have, which is that I'm going to declare that I only fill. So what I have to say is what is the non-perturbative version of the Fermi C. So I have to say which state I fill, and I will declare that I only fill energy eigenstates of the fermion that are scattering states that look like the one that's depicted here. That is, you have some fermion coming from the right, they bounce off, and there's some amplitude of tunneling. So this is a well-defined scattering states of this form. There's another scattering state where the fermion coming from the left. I do not fill those states. So I only fill this state. Now, with this, from this perspective, the vacuum, I want to interpret this as the vacuum of the Siegel-Swan matrix model. So this vacuum is perfectly stable. It's by construction energy eigenstate. But the question now is, what are the excitations? I have to talk about particle hole excitation. I claim that with this closed string vacuum, the natural excitations on top of the vacuum, which are the particle hole pairs, are such that the reflection amplitude of the hole is the inverse of the reflection amplitude of the particle. And this sounds a little strange because the particle tunnels, so the reflection amplitude of the particle has amplitude that's slightly less than 1, modulus slightly less than 1, and the reflection amplitude of the hole has amplitude slightly bigger than 1. But in some senses, this also kind of makes sense intuitively because there were already a hole on the left, and the hole wants to come back out from the left to the right. So there's some kind of stimulated reflection of the hole. So this is the key to the whole business of this non-perturbative complete Siegel-Swan matrix model. I'm going to now take this as a given. The reflection amplitude of the hole is the inverse of the reflection amplitude of the particle, and proceed and calculate the scattering amplitude of the particle hole pairs. Now, the reflection amplitude of the particle, which this is a standard exercise of non-relativistic quantum mechanics, this formula is well known. Now, this formula actually contains, it's relatively simple, some square root of Rachel gamma functions, but contains a lot of information. So, let me point out that this E is the energy of the fermion, of the particle, normalized so that the top of the potential is energy 0. So we're talking about energy minus mu plus some order 1 amount. So the order 1 amount would be the energy carried by the actual particle hole pair. The mu, remember, is goes like 1 over G string. So, e to the 2 pi e, this factor here, for example, is non-perturbatively small. So this correction factor 1 over 1 plus e to the 2 pi e is like a non-perturbative correction, whereas the rest is sometimes perturbative because, in fact, it is going to be, one can show that it's going to be the Borel summation of its own perturbative expansion in 1 over mu. And there's some formula that relates the particle and hole reflection amplitude to the actual scattering amplitude, which is does not necessarily consider particle numbers. You can have, for example, here the 1 to k scattering of the closing modes, which are the closed string amplitude. So this is what I'm going to be shooting for. And I should mention also that if you actually plug this particle hole amplitude into this formula, with the reflection amplitude of the hole to be the inverse of the reflection amplitude of the particle, you'll find the following structure of the expansion in 1 over mu. So this is the result you get from the matrix model. That is, there's a perturbative series. This is the well-known stuff. It goes like 1 over mu, the string coupling to some power like genus expansion, and these perturbative amplitudes at each genus G is some polynomial expression in the energies that are known. And then on top of that, because of this 1 over 1 plus e to 2 pi e factor in this reflection amplitude of the particle, you could plug into this integral, you'll produce a instanton-like expansion in powers of e to the minus 2 pi n mu, and this is the same as e to the minus 1 minus n over g string. So this looks like an instanton expansion, but interestingly, at every instanton order n, there's a further expansion in powers of 1 over mu involve not even powers of 1 over mu, but both even and odd powers of 1 over mu. So this is what looks like an open string expansion as opposed to a closed string expansion. They come in powers of integer powers of g string as opposed to g string squared. Okay, and I should say that one can see explicitly that in this context that there are no e to the minus 1 over g string squared effects. So this is presumed an accident of sequence string theory, at least within the closed string sector without FZD brain. Okay, so now for the rest of the talk, we'll turn to the worldsheet formulation of the D-instanton mediated closed string amplitude. Now, as I said, the logic is that we have D-instantons in space-time, which are localized in space-time, and on the worldsheet, there are boundary conditions. So we would like to consider such diagrams that will be corrections to closed string scattering amplitude. So what are the D-instantons? In sequence-1 string theory, the simplest class of D-instantons are so-called ZZ instantons. So you take the Dirichlet boundary condition in time and the tensor with some boundary condition in Liouville theory. Now it's well known that boundary condition in Liouville theory can be decomposed as direct sum of either ZZ or FZT boundary conditions. But FZT boundary conditions, they look like branes that are semi-infinite in space-time. As instantons, they will have infinite action. They will not play a role in my story here. The only kind of instanton that will potentially contribute are the constructed from the so-called ZZ branes in Liouville theory. So heuristically, you can think of the instant action as minus of the disk diagram. Now, in Liouville theory, it's a little tricky how to compute this diagram, but in fact, you can identify the instant action as that of the bounce of the fermion in the dual matrix model. And the instant action is indeed 1 over GS, which is exactly expected from the action of the bounce, just semi-classically. Now, this is actually not the full story. Of course, there'll be also multi-instantons and so forth, but there's more. In fact, in the 99 paper of Zamolodchikov and Zamolodchikov, where they discovered the ZZ boundary condition Liouville theory, they found a more general family of ZZ boundary conditions labeled by a pair of integers m and n. So they're integers starting at 1. And you can represent these boundary conditions in terms of boundary states. They are some integral of the Ichibashi states spewed out of the Liouville primary with some disk 1-point function we call psi. And explicitly, they take this form. So this is the formula for this 1-point function, and this completely defines the boundary condition. And this was discovered by looking at the modular bootstrap from the level of the cylinder diagram. Okay, so I'll refer to the D-instantons constructed out of the Dirichlet in time, tensor with the m, n type ZZ brane to be the m, n ZZ instanton. And one can argue by that they correspond instantons with action that is m times n times that of the basic 1 ZZ instanton. The argument basically has to do with thinking about the action as proportional to the disk diagram. But usually we have to have some insertion of this diagram. But formally, if you continue this momentum to I, the VP behaves like identity operator, even though it's not part of the spectrum of theory. So this is a bit of a hand wave argument that suggests that the m, n ZZ instanton in fact has this value of the action. So the point is that we may have the m, n ZZ instanton, and if they contribute, they'll contribute as if they look like m times n number of instantons, of the basic instantons. In fact, by matching the answer with the matrix model, we'll conclude at the end that only the m, 1 Z instantons will contribute for all integer m, positive integer m, and multiple of configuration of such instantons. We don't have a clear understanding of why it is only this subset of the positive Z instantons that contributes, but this was an unambiguous conclusion by matching the answer with the matrix model. So let me now discuss the one instanton contribution, what it looks like. This was, in fact, already alluded to in Ashraf's talk. So I'm going to consider the simplest non-trivial amplitude in this sequence-1 string theory. We just have one closed string coming in and one closed string going back out of the Liouville wall. Well, this is non-trivial already at level of perturbation theory. but I will not have the time to discuss the perturbative part of this. I'll just consider the one-instanton contribution, which is non-perturbative at order e to the minus 1 over gs. So the diagram that's relevant at this order is two disks. Each disk has one insertion closed-string vertex operator. I mean, of course, there can also be some disconnected pieces, which I will not, which will be taken into account shortly. Disconnected pieces without closure insertion. So this diagram looks disconnected, but it's in fact a contribution to the connected amplitude because the boundary of the two disks, they end on the same Z-instanton. And it is on each individual diagram, the energy is not conserved because the instanton is localized in time, but the energy conservation is restored after you integrate over the collected coordinate x0 of the instanton, the position of the instanton in time. So the contribution of this to the amplitude takes the following form. So there's integration in the collected coordinate dx0. In this case, it's just time, that's it. And you have e to the minus instanton action, which, as I said, is just e to the minus gs, or e to the minus 1 over gs. And then you have these two disk one-point diagrams. After fixing the Sapon-Killing group and all that, you can carefully fix normalization. And they look like e to the I omega x0 stinch pi omega. The stinch come from the ZZ boundary state, this one-point function in Liouville theory. And e to the minus I omega prime x0 stinch pi omega, where omega and omega prime are the energy of incoming and outgoing closed-string state. Now, there's overall normalization, which I don't know how to fix, but I'm going to assume that it's a universal constant. I'm going to try to fix it by matching with the matrix model. Well, this is very easy integral to do. You get the delta function of energy conservation. You have the e to the minus instanton action, and then you have the sinh square, which Ashok already mentioned. It turns out that if you take the proposal for the non-perturbative completion of sequence-1 metric quantum mechanics that I described earlier, and just expand to this order and check the sinh square dependence indeed agrees. Looks quite simple, but actually it's already extremely non-trivial because it agrees with my proposal for the sequence-1 complete matrix model, but this actually disagrees with type 0b matrix model. If you take the type 0b where you take the, so here it's important that the whole reflection amplitude is a particle inverse. If you take this type 0b matrix model, actually it disagrees, okay? So that's why we thought that we came up with this proposal. This overall normalization can be fixed to be some constant. I should say this constant is universal, but for the Z-instanton of the 1,1 type, the most basic type, for the other m,1 type, as we'll see, there's a different normalization constant. I mean, a priori, we don't know what the normalization constant is. In fact, you could wonder that maybe there's a version of sequence-1 string theory where there are no instant contributions, where this ends are just 0. That will be problematic from the point of view of the matrix model, but I will not say any further about that. But if there's question at the end, we can discuss that. Going to next leading order, still for the one-to-one closed-string amplitude at the one instant level, you have contribution of order e to the minus 1 over gs times gs. So in this case, there are 4 diagrams that are of this order, just naively. There's a disk with 2 closed-string insertions. There's a disk and an annulus. Each one has 1 closed-string insertion. The one with the 2 closed-string exchanged. And then finally, there's a diagram which I had before, but together with the additional disconnected piece, which is a disk with 2 holes. In fact, this was also a subject of Ashok's talk. So let me describe this in my perspective here. The first 3 diagrams, each one has an open string divergence from this open string channel. And this divergence is due to the open exchange of open string Clevey modes, is of a logarithmic type, and is kind of fatal at level of each individual diagrams, but it's understood that there are the exact same divergence between these different diagrams that will cancel each other. This was observed by Poshinsky in '94. After canceling this log divergence, you're still left with a finite ambiguity. Now, of course, there are also going to be power divergences due to the exchange of other open string modes off shell. here I'm going to treat them in a naive way. So the approach I'm taking here is analogous to what ordinarily the sort of on-shell approach to string amplitude, it is usually the quick way to write the answer, although not completely rigorous. Whether the completely rigorous method is the open classical string field theory that Ashok has described. Okay, so the upshot up to this point is that if you just follow your notes and do this worksheet computation, there's a finite ambiguity in canceling the log divergence due to the exchange of open string collective mode. And then there's also a diagram, there's a constant coming from this with two holes, which you can view as a ordered G string correction to the instant action. This thing will be very, from the on-shell perspective, I can't really give a number, unambiguous computation of the diagram. There are all kinds of divergences you have to regularize, and we don't quite know how to regularize in a consistent way. It really seems to require open plus closed string field theory to get this. But I'm going to proceed here just by assuming that these two ambiguities are some finite constant. I'm not going to be able to, in this talk, tell you how to fix it from the worksheet prescription. We're going to try to fix it by matching with the matrix model. Now, Ashok has actually described in his talk how to fix the second ambiguity, and it actually will agree with our conclusion here. So as I mentioned, there are two paths forward. So Ashok's approach is to try to fix this constant from open plus closed string field theory. It's a rigorous approach. It's an approach that you should be taking. It takes a lot of work. We are going to take a shortcut. We're just going to fix in this case, we're just going to fix the two constants by matching with the matrix quantum mechanics. In fact, the computations, if you want to match with the matrix quantum mechanics, you have to compute the whole thing. And to compute the whole thing is quite hard. We can only compute it numerically. I will say in a moment where the complication is. But we did this. And we can match with the matrix quantum mechanics numerically by splitting two constants. And to the extent that Ashok has computed this constant from open plus closed string field theory, they in fact agree up to numerical error. Let me say what the result looks like. So the matrix model, if you just take this formula I wrote before, the integral of the particle and whole amplitude, expanding to this order, you get a contribution to the one-to-one closed string amplitude at order e to the minus 1 of gs times some function of the energy, which is this function. Okay, it's not too complicated, but sufficiently non-trivial. And we can try to check this against the matrix model, the worksheet computation, which I described, that's unambiguous up to two constants. So by fitting two constants, here's the actual numerical fit. Okay, so this is for imaginary omega for reason of regularization. And the red dots are the numerics. So you see that they're in complete agreement. The numerical error mostly coming from the fact that it's kind of tough to calculate this annulus one-point function in Liouville theory with this boundary condition. The only way we know how to calculate this is by integrating conformal blocks. So we know the disk pulse boundary, one-point function and things like that, the false three-point function. So you can decompose this annulus one-point function in Liouville theory in one or the other channels of the conformal block decomposition and just integrate this conformal block. Now, thanks to work I did 2 years ago with Min-Jae Cho and Scott Collier, I think it's actually maybe 17. We have some, method. We came up with a method to extend what Zabolochkov's recursion relation was for the torus for the sphere full-point function. We extended that to the torus for and also higher genus Virasoro conformal blocks. And this method allows us to efficiently calculate these torus two-point Virasoro conformal blocks, and then we numerically integrate them over the moduli space, as well as the internal Liouville momentum. But this is a pretty tough integral to do, and that's the main source for the 1% numerical error in this computation. Okay, so that was the one-instance story. Now I'm going to discuss the multi-instance contribution. So as I mentioned earlier, we may need to include this more general D-instantons. It turns out that only the M,1 type will be needed. The multi-instanton moduli space, in sequence-one string theory, we're lucky that each individual instanton in the moduli space is just aligned the time x naught. So for multi-instanton, you'd expect the moduli space is just the collective coordinates. I just parameterize by the coordinates of the time coordinates of each of the instantons. They can be of different types. And importantly, if you look at the general structure of the worksheet expansion, you expect that there'll be some correction to the measure factor that's of order 1 in G string. That looks like the exponentiation of the annulus diagram. Okay, so what does this do? Well, let's examine this. This becomes non-trivial.
You have 5 more minutes.
Okay, thank you. So this is kind of non-trivial when you have 2 instantons at different positions at x1, x2 in time, which I labeled by the red and the blue boundary. Okay, so in this case, well, this annulus diagram is fairly easy to calculate in the worksheet CFT. It's the integration of the modulus t of annulus. There's a trivial part that involves some 1 over eta function. There's the x0 part that depends on the separation of these 2 d-instantons in time. This delta xe, the separation in Euclidean time. And then there's the BC goes contribution. This eta functions all cancel, and this integral is very easy to do. It just gets 1/2 the log of this simple expression. Okay, so now if you exponentiate this, actually there's twice of this because the string is oriented, you just get this correction to the measure factor. So the numerator, delta x squared, can be interpreted as a minimum determinant. So you expect some non-abelianness of the instantons, even though here we're integrating only over their individual collective coordinates. But then there's the denominator, which has to do with the fact that if you separate this by 2 pi, the basic instantons by 2 pi in Euclidean time, there's actually open string tachyon pole. So if you are to integrate over the collective coordinates in Euclidean time, you're going to encounter this pole, and you have to come up with a contour prescription. That's part of why it was non-trivial to understand this dictionary, how to do instant computation in this theory, because there are these singularities on the naive instant moduli space. And here we consider a simple prescription, which is simply to rotate this to the Lorentzian contour, and that avoids all the poles, it turns out. So for Lorentzian time separation delta x, this is the instant correction to instant measure as 1 loop order, open string 1 loop order. Okay, so our prescription will be, we're going to integrate the instant moduli along the Lorentzian contour for each of these instantons. This is equivalent to some kind of IF prescription if you want to insist on working with Euclidean contour. It doesn't matter. And we integrate over all of these. There's some subtlety of the vacuum transition amplitude normalization you have to worry about. I won't discuss that in detail. I'll just show you that the structure of the 2-instant contribution to, say, the 1-to-1 amplitude at order e to the -2 over gs, it looks like this. There's contribution from these similar kind of diagrams, now with the boundaries that can both end on the same instanton or on a different instanton, and you have to integrate over the position of the 2 instantons. And there's the normalization factor associated with the 2 instantons of the 1,1 type. Now, there's also additional contribution coming from instanton of the 2,1 type, because as I said, a single instanton of 2,1 type actually has the same as action as twice the instanton of the 1,1 type. So this contribution here with the unknown coefficient N2 up to now, and we'll try to fix that by matching with matrix model. So one can do this more generally for any instanton at the leading order e to the -1 n over gs. I mean, generally there will also be some gs with some open string loop order. We're going to just work at the leading order here in the open string expansion. The general structure looks like there's some formula. I want to explain how you get this, but it's just coming from doing this integrals very carefully. There's some combinatoric formula which looks like some kind of instant sum. These are the instant types. Okay, so there's some non-trivial combinatoric formula. And from the matrix quantum mechanics, if you just take the prescription I gave you and expand, you find a result at this e to the -n over gs order for the 1-to-1 amplitude that looks like this. There's some so the important thing is the energy dependence here, and there's some hypergeometric function, but actually this thing truncates to a polynomial, and it doesn't look obvious, but actually these 2 expressions, they're the same by some combinatoric magic, some combinatoric miracle, and that was seems to be provided that you fix the set of constant normalization constants to be this. So this is the normalization constant for the instanton of the m,1 type. So this agreement is extremely non-trivial. It actually requires some combinatoric identities that we can only check on Mathematica. We cannot actually quite prove in generality, but so it works. Okay, so let me conclude. The conclusion, first of all, is that based on this agreement, we think C = 1 string theory defined by the worksheet genus expansion amended by the D-instanton effects in the way I described is actually non-perturbatively complete. Now, in what sense is it non-perturbatively complete? So far, we have restricted our discussion to exclusive closure amplitude. And it's not quite saturated in unitarity. This can be seen explicitly from the instant contribution, actually. But physically, it has to do with the fact that the closed rings are particle hole pairs. Now, the reflection amplitudes correspond to the particle hole come in and bounce back out to the right side. But you can have a process where the particle tunnels to the left side and hole goes back out to the right side. So this does not correspond to a closed string state. This corresponds to some kind of new non-perturbative state that my best guess in C=1 string theory, from the string theory perspective, is that it's some kind of ZZ brane that kind of rolls to the wrong side. So it's kind of the ZZ brane with open string tachyon that's rolling to the wrong side. So presumably you have to include these additional states to make the S matrix fully unitary. But nonetheless, we believe that the D-instanton corrected exclusive closed string S matrix elements were actually exact, even though they do not quite saturate unitarity. Now, we're a bit lucky here because the D-instanton contribution is unambiguous thanks to the Borel summability of the perturbative series, because you have to say what the perturbative contribution is before you draw out a non-perturbative correction. And also it just happens that there are no sort of non-perturbative gravitational effects, which will be of order e⁻⁻⁴ and this is special to C=1 string theory, of course. But even in C=1 string theory, this may not hold if you extend the theory beyond the closed string sector by including FZT brane and having to do with non-single sector matrix model and black holes and so forth. This was brought up earlier at the end of Asho's talk. Finally, let me just say that there's some generalizations one can do. One can extend this to finite temperature and study the 0B version of this, which is very interesting. There's some lessons to be learned for critical superstrings. In fact, two of these are also mentioned as interesting directions in future in Asho's talk, and these are things we're currently thinking about. Thank you.
Thank you for the beautiful talk. So I'm going to briefly unmute everyone. So I hope the audience can join me uploading sheet. Okay, so now we have time to take question. So let's see, I need to unmute. I cannot unmute Chi.
Okay.
Yeah, you can unmute yourself. Excuse me. So so Andy Strominger is raising a hand, so I'm going to unmute him. You can ask question, Andy.
Yeah, can you hear me?
Yes.
Yes.
Oh, so does this incisive non-perturbative understanding of the C=1 string theory, I guess it's like 30 years later, does it, are you able to say anything about whether or not it contains black holes? And if not, what would can we settle that question? And if not, if this analysis doesn't do it, what do we need?
My understanding is that there is no black hole in the closed string sector of C=1 string theory, but the path to, but doesn't mean that you cannot have black holes in C=1 string theory. You have to be a little careful what you mean. The point is that in the Hilbert space of the closed string sector of C=1 string theory, I believe that the black hole is nowhere to be found, which is equivalent to saying that the black hole does not exist in the singlet sector of this matrix model. But I do believe that there are black holes if you go beyond the single sector matrix model. In fact, there's a strong hint for this already that was pointed out in one section of Huang's paper in 2005. It took me a long time to understand what he was talking about in that section, but now it seems to me that it's really the natural path to the black hole, which is that you can extend the theory by include, first of all, the FZT brane. These FZT branes, they change asymptotics. So you should think of them as not states in the same Hilbert space. They change asymptotics, and you take a large number of them. So the picture looks like this. So you have this linear direction, and you have FZT branes that kind of extend up to here. Okay. You take a large number of them, but you push all of them to infinity. So there are NF of them, but you kind of send them retreat to infinity in such a way that their influence. So the open strings are living on the FTD brane, but because they're way out at infinity, it should still be a pure closed string background. But when NF is large enough, their influence remains on the closed string. So one can take a decoupling limit, a suitable decoupling limit, which Juan discussed in his paper, and it turns out that the decoupling limit only is non-trivial at finite temperature. This is a subtlety that is something we're currently thinking about. I won't be able to go into too much detail, but the proposal is that after taking this decoupling limit, you get a one-parameter family of deformation of C=1 background at finite temperature that can interpolate between the usual vacuum and the black hole. And you can then ask, what does this mean in the matrix model? And I think what it means in the matrix model is that you have to extend the matrix model to include arbitrary power of tensor power of adjoint representation, and in which you'll find arbitrary number of long strings, and the black hole should be due to a thermal bath of long strings in the matrix model. This is something we're currently trying to work out in more detail.
Okay, so now Shiras Miwara asked question. By the way, when you want to ask question, I would recommend you to raise hand rather than write into a chat box, because it's hard to identify a person out of 360 people. So raising hand is preferable. So I'm going to unmute Shiras to ask for him to ask question.
Aiji, you chose one particular non-perturbative sort of completion of the matrix model, and found agreement with standard worldsheet string theory. Now, it would appear that there are many possible non-perturbative completions of the matrix model, all of which have the same perturbative sector. So it seems to me that there are two possibilities. One is that there are many worldsheet sort of completions. There are many parameters of the worldsheet theory that have different rules for non-perturbative completions to match the other completions of the matrix model, or there's something special about the completion that you chose on the matrix model side, that only that or that and a few others have a worldsheet string theory. So I wanted to know, firstly, is this dichotomy correct? Is it one or the other? And second, if so, which do you think is true? And
I think that's an extremely reasonable question, and I don't have a good answer for that. I guess one thing I could say is that so far in this approach, which we follow our nose and try to collect the D-instanton contribution in worldsheet and try to match with the matrix model, one a priori ambiguity is this normalization. Now, Ashok at the end of his talk suggested some way to fix normalization by considering brane anti-brane. Barring that, if you cannot fix normalization, you might think that you might wonder whether you can have some just other matrix model completion that will match with the D-instanton computation with different normalization. So this I'm not sure about. The things we tried did not work. Other completion we tried did not work. But there's one thing you can say, which is that if you imagine that you have a way to define C=1 string theory that has no instant contribution at all. So what's wrong with setting all this normalization constant to 0? Okay, so if all these conventions are 0, and there will be no contribution for D-instanton, so what's wrong about this? And what's wrong about this? Well, not obviously anything wrong from the string theory perspective, but there's something funny from the perspective of the matrix model. From the matrix model, you see, these are constructed out of the non-relativistic free fermion system with this reflection amplitude. To throw away the instant correction means it will be equivalent to drop this part. Okay, if you drop this part, that's equivalent to throwing away the instant correction. If you drop this part, this amplitude, I claim that cannot be the reflection amplitude of any non-relativistic particle, because on the complex energy plane, it has branch cuts instead of poles. So it violates the property of non-relativistic quantum mechanics. So I would say that if you want to have a quantum mechanical matrix model dual, this suggests that there has to be D-instanton effect. Now, I cannot precisely tell you what is the most generous possibility that is allowed. So we try something that happens to work.
thanks.
So now Emil Martinez has a question. I have unmuted him.
Yeah, so I had a question about the higher ZZ instantons. So
yeah,
so the closed string modes are composites of the underlying fermions, And so I can imagine those multi-instanton processes you're describing are where the collective field is connecting to multiple eigenvalues tunneling under the barrier. Is it correct to interpret the m,1 instantons as processes where a single eigenvalue bounces several times under the barrier before it tunnels back out?
There might be an interpretation like this, but I cannot really, I don't know for sure. A part of the issue is that I feel like this might also be tied to the contour prescription, exactly how you avoid the singularities on the modular space here, which was the Lorentzian contour, that might affect what you call this higher instant contribution. So there might be such interpretation, but I don't understand that yet.
And do you have any understanding? Do you have any understanding of why the other m,n instantons are not present?
No, we don't, except that we can assume that they contribute with some coefficients, and by matching with the matrix model, can explicitly see that the coefficient has to be 0 because the contribution are distinct. But from the worksheet a priori, we don't know how to see that. I mean, presumably, it might have something to do with the number of passing modes supported by this, and if you have some way to think about the full non-perturbative open string path integral, open string field path integral, you might be able to understand that, but we're not there yet.
Okay, thanks.
Okay, is there any other question? Okay, if not, I'd like to thank Chi again for his talk. And we have about 9 minutes break. And so we'll meet again at 6 p.m. in South Africa time. And